So hello everyone, welcome in this 12th edition of the KIKK Festival. This is the second conference in this French room, and it's the first in English. So this morning it was in French, and today it's in English this afternoon. I have some announcements to make before we can start. So don't forget to download the app Subcard if you want to meet some nice people and do some matchmaking with people in your fields. Don't forget to check out the program of the workshops, because we have still some places left, and it's on Saturday. And so today and now we are welcoming Laser Talks, Brussels, organized by Alexandra Dementieva, and we will welcome DMITRY GELFAND, EVELINA DOMNITCH, YOANN OLIVIER, and it's moderated by EDITH DOOVE. So give them a warm welcome and enjoy the talk.
Hello, welcome. So it's very nice to have you here, even if it's very rainy and not very good weather. So I hope that you will continue watching our laser talk, because we do it quite often, like at least 4 or 5 times a year. And so now I will give a floor for our panelists, and I will give it first to EDITH DOOVE, and she will present everybody.
Thank you, Alexandra. Welcome. This is actually our 11th talk, and we're immensely happy to have been invited by the KIKK Festival, which is really nice. As Fanny said, we have EVELINA DOMNITCH and DMITRY GELFAND as artists. This talk takes actually the innovative project Lemniscate Cascade as a point of departure, and in this project, that could be both described as an installation and a performance, artists and scientists join forces to unravel the secrets of light-sensitive liquid crystals. This enigmatic material is more than just the stuff of digital displays, but holds the key to the fundamental dialogue between light and soft matter that sparked life to Earth. Life on Earth originated in an intricate dialogue between light and soft matter, liquids, colloids, polymers, foams, gels, liquid crystals, flesh, and numerous other biological materials. Liquid crystal flows like a liquid, but it is structured like a solid latticework. It has been broadly implemented as medium for flat panel displays, yet the commonest example of this two-phase condition is DNA, the molecular foundation of living matter. And we also have Professor YOANN Olivier. Your Imagine researches the future of OLEDs that are at the forefront of lighting and display technologies, but there's always room for improvement. This project delves into the world of TADF, thermally activated delayed fluorescence, to boost OLED's efficiency to an astounding 100%. It's a quest to understand the intricacies of singlet and triplet states influenced by magnetic field effects, MFEs, such as spin-orbit coupling, hyperfine interaction, and the delta-G mechanism. You're going to tell us all about that. Olivier's multi-scale approach tackles these challenges, offering new perspectives for material design. So, as a moderator, I'm hyper curious to hear more about this myself. I hope you too. But we will start with EVELINA and DMITRY. You create installations and performances that merge physical phenomena with uncanny philosophical practices. To investigate questions of perception and perpetuity, you employ current findings, particularly regarding wave phenomena, of which Lemniscate Cascade is an example. And can you first, before we get to Lemniscate Cascade in particular, tell us more about your work? I think you've prepared your presentation, and so and I hope you will tell us something about how you decided to collaborate together, for instance, and what was the first work you made together.
We will certainly answer those questions and then some.
Yes, but so I can also start that answering your question from the back. So Dmitry and I met more than 25 years ago in New York City, and that's where we had our first exhibition. But none of us was doing the kind of art we started making together. So I was studying philosophy. I was doing a PhD in philosophy, and Dmitry was graduating from a film school.
Oh yeah.
But when we came together, we decided to engage in this type of art, which was a blend indeed of the phenomenological research or questioning your own perception and matching it up with the current findings of science, which are very counterintuitive, counter experience, and counter perception. So
Okay.
and I also would like to say a few words about the great topic of this year KIKK Festival, Bodies of Water. And the work of Dmitry and myself, more than 70% of our works, installations, or performances, water is the main material. Water, liquids, and when we met in New York City, we came to these constraints in our practice, and the departure from solid media was one of the first. And that's why working with liquids, fluids, gases, sound waves, light waves was a very natural decision. And the reason for this constraint is that we wanted to unveil through human senses, through experience, the wave nature underlying our reality.
And also to depart from art's age-old infatuation with the illusion of solidity and permanence.
And objects and objectification of reality, which is another trick of consciousness.
So the first artwork where we were able to address all of these constraints was a piece called Camera Lucida, Sonochemical Observatory, an artwork that probes an exotic physical phenomenon known as sonoluminescence, where high-frequency sound waves propagate through a gas-infused liquid and cause the gas, if it's water, this would just be air that is dissolved in the form of bubbles within the water, to collapse, to implode, at which point temperatures as high as are found on the sun are reached, and light is emitted. Light, which takes the shape of those sound waves, allowing us to observe sound three-dimensionally in total darkness.
And here you see the apparatus itself. So it's a bowl, it's a 60-liter container with water, which was the largest scale on which sonoluminescence was performed, displayed, because in the lab it's usually done within 200 milliliters, 100 milliliters, usually observing a single bubble. So here is our first work with water. And this is a work hydrogeny, where we using laser light, scanning laser light, to observe very intricate bubble architectures of water while it splits into hydrogen and oxygen. And here is a work called Force Field. It's a performance, and we are levitating droplets of water on acoustic standing wave. This is another work with water, where we again use this magical interface of bubbles. And here it is called Time Synthesizer, and the topic of this work is turbulence, another quite fascinating natural phenomenon where matter starts organizing itself.
So we're going to leap from hydrogen microbubbles to macroscopic soap film clusters, bubbles that are in fact precursors of the cellular membranes that allow for life to be possible. So in 10,000 peacock feathers and foaming acid, a single laser beam, we would say white beam, but it's also composed of several diodes, enters the skin of a soap bubble. And when that happens, instead of what one might predict, where the light simply goes through the transparent medium, instead it gets trapped inside of the bubble skin, creating so-called polariton solitons, surface waves that are that essentially electrochemically couple the light to the film, and the light carves these surface waves across the bubbles, such that they make these micron thin optical tracks, each of which can create a large scale projection of molecular dynamics happening in the film.
So these spectacular projections that you see are done with a single laser beam that is trapped, is going through a tiny soap bubble. So this projection mechanism that we developed in relation to this work, we are also using in the work with liquid crystals we will talk about later.
But this is also liquid crystal. In fact, most people might have come across the fact that soap film is an example of lyotropic liquid crystal, a situation where the phase transition into this state of liquid crystallinity, this state where everything has orientational order but also flows, is dependent on the concentration of one compound within water, usually for biological systems.
And maybe you can talk a little bit more in detail how soap film is a precursor of a living cell.
Well, yeah. Well, what's amazing is that you have this bilayer forming, this sandwich of sorts, which consists of water, and within that water you have hydrophobic and hydrophilic molecular chains.
Ions, so they have a bit of a charge, and they can align according to this charge. So it's a geometrical configuration of these bigger molecules, and just having the slight charge and aligning on both sides, they can create a proton membrane. And this is what soap film is. And an incredible thing about soap film is that this film between this layer of ions can become one molecule thick. So this is a kind of optical spaces you can observe with just this very simple technique. And the projection,
Maybe we can turn the lights down when the video is fine.
Yeah, because we can see it quite well on this screen, but on the projector it's all washed away.
Est-ce que vous pouvez peut-être la lumière, si on peut éteindre, oui, merci.
using any recording medium was one of our constraints. I just want to remind you that this is not a video projection, this is a live optical projection of what is happening in the soap bubble scheme at the moment of the performance, just with a laser beam. And a few years ago, just before Corona, we had an amazing opportunity to participate in a Studiotopia project where we could select among 20 scientists, and residents to work with us in our studio. And one of the scientists we selected is from Brussels, Guillaume Schweiger, and we also selected another scientist from Amsterdam. And together with them, we developed Lemniscate Cascade, a work with liquid crystal. In fact, while working on this Studiotopia project, we pursued 3 different directions for an artwork, and we managed to create one artwork. So one of the directions led to an artwork. The second one, we are kind of halfway, but these are the 2 artworks that we are still developing for the future, and we will talk about all 3 of them.
So in Lemniscate Cascade, we take advantage of the fact that liquid crystal is so responsive to various environmental stimuli. In this case, it exquisitely responds to light, both in terms of the wavelength of light involved, polarization of the light, and of course the intensity of the light, which can create temperatures that cause the liquid crystal in some areas to undergo a phase transition into its liquid crystalline state, and in other portions going into a purely liquid state. And this transition is something that also drives a vast variety of other phenomena. Namely, we're able to see how the light creates vesicles within the liquid crystal and even vortices. And although we will shortly discuss this, the ability to create a vortex with light is something that was pioneered by means of liquid crystal. Devices such as are called spatial light modulators allow one to very, very scrupulously define in 3 dimensions the properties of a given light beam. Perhaps we should watch a video documentation.
Well, yeah, so we can just, indeed, this is something that we developed as an installation, but then we realized, that it works slightly better as a performance, because indeed this phase transition happens more or less within room temperature. So controlling it live creates even more dynamics, and we usually perform it live. So all the morphological changes, all the changes you observe in the movement of the liquid is all activated by laser light live in real time. And the structures, the morphologies you see is the interaction of the liquid crystal with the laser beam. So again, with this very simple means, just having a laser beam, we can observe, in fact, molecular dynamics with a naked eye on a microscopic scale, which we find quite amazing. That liquid crystals are such magical materials that can unveil the molecular world on a microscopic scale.
So one of the endeavors that we were very, very close to realizing involves the formation of Archimedean spirals.
Or spiral waves.
Yes, akin to the kind that you will encounter in the Belousov-Zhabotinsky reaction, except for that in liquid crystal, only one researcher that was able to achieve this, Ivan Smolyuk at the University of Colorado, Boulder, by means of polarized light, causing in real time, unlike the Belousov-Zhabotinsky reaction, in real time you can observe these spiral waves forming, and the closest that we got was, you can observe in this video fragment here.
And this is shot under a microscope.
This was done with the help of Guillaume Schweiger and Adam Shafai at the Université Libre in Brussels. So you ask, why do we want so badly to see these spiral waves?
So spiral waves are extremely interesting phenomena, quite ubiquitous in the universe among living and non-living matter. So you can see them in crystals, you can see them in Belousov-Zhabotinsky reaction, which is so far the only known chemical reaction, or let's say chemical oscillator. So it's a reaction that is not exhausted once it runs once, but it will keep running, well, not indefinitely, but oscillating for a long time in one direction and the other. In living matter, these spiral waves, they appear in a cell when it's fertilized and the embryo starts developing at the very first hours of the development of a cell.
That was actually, for the very first time discovered and documented by a group at MIT only a few years ago.
So this fertilized cell will start, before anything happens, it will start producing this. They're also sometimes called autowaves, or these spiral waves on the surface of the cell. And this is how the first stages of development happen. Slime mold, various unicellular organisms, when they group together into the first prototypes of multicellular organisms, they communicate via these spiral waves. So we find this Archimedean spirals, this very beautiful geometric pattern, to be fascinating. And though you can see it under a microscope with this Smolyuk experiment, and you can see it in Belousov-Zhabotinsky reaction with time lapse when you shoot it and then play it back very fast. we want to use laser light, direct laser light, and to make a real time projection of
Yeah,
a liquid
not under a
crystal.
microscope as you see it here, but
And
as
so-
in the case of,
Yeah, so that was our second project we were pursuing, and we're sort of halfway. And the third, so we will end with our third project we wanted to do that we're working on at the University of Amsterdam with Florian Schreck.
Yeah, there, instead of looking at a projection of the liquid crystal navigating light
or
navigating
being
liquid crystal.
activated by
Yeah.
light.
I mean, one way or the other, it's always a feedback mechanism that we're curious about. It goes in both directions. So we would like to look at optical vortices. Now these are actual twisted light beams in a liquid crystal environment, directly in a bath of liquid crystal. This is
In a colloid.
Yes, indeed. In a liquid crystal that also has some other particles in it that trace the flow patterns and the movement of this twisted light. And once again, we return to this twist and to these spirals because one of the most fascinating things about the primordial soup was when a liquid crystal, very much akin to the kind that we used in Lemniscate Cascade, started to twist as a result of polarized light, and this twisting is what eventually led to the double helix in DNA. You have this chirality, this handedness that definitely arose through this dialogue between light and soft matter.
And just a few words about the name of the work, Lemniscate Cascade. So Lemniscate is this perfect geometric figure. It's an infinity sign or a number 8.
Or a bow tie.
Or
as it is
bow
also
tie,
been called.
and it is also very closely connected to the morphology of light propagation, and the liquid crystal is able to visualize it. So we've seen in the video how it creates this kind of oscillating bow tie, and sometimes we can get it during the live performance very, very precisely, that you really see it as this bow tie. And sometimes it will create this beating heart, something that is beating, pulsating, also very much akin living creature. So thank you very much.
Okay, thank you. We will take questions from the audience at the end for practical reasons, but this was fascinating already. And while YOANN is installing, because maybe we haven't been too clear, but I think from their talk it became clear that laser talks are about art and science and the connection between it. And while YOANN is installing, maybe EVELINA, Lemniscate Cascade has also a clear soundtrack, or maybe you work with sound as well. Can you tell a bit about that? Because do you follow the rhythms at the same time? Because it's a live performance, you said. Is the music or the sound also emanated live, or do you respond in one way, or is it a program that is connected, or how does it work?
Yes, so another phenomenon we are fascinated with is synesthesia.
Yeah.
So we always, when we work with sound, we always try to create some kind of dialogue feedback system with the visuals. And since the visuals are all created live and not so much from our own ideas, they are the manifestation of natural phenomena and their interaction with light. So we developed a special software that reacts on movement, the measurement of movement and brightness. And this software analyzes the visuals in real time and alters the library of sound that we prepare for the performance, and it is also being adapted live to the sound, to the acoustic properties of the space.
Yeah, there's nothing automated about it, but it's a system of analysis with the camera and the software environment.
Yeah. So, and it stresses also this idea of what you want to show in your work, this notion of things changing all the time, the ever-changing character of life in the end. So also not only in image and in sound, I find it fascinating the twists that you talked about, which is at the origin of life. But YOANN is going to tell us, you're all ready for so I hope you can, so from a scientific or purely, because you are scientists as well in a way, the way that you work, but you work in a particular scientific way, so you can maybe explain us a bit what liquid crystals.
We don't have to publish papers like scientists.
Oh yeah, that's the advantage. Yeah.
That's an advantage for sure. So my name is YOANN Olivier, and I'm coming from the University of Namur. Are you okay? Okay, great. So I'm coming from the University of Namur, and so I'm a member of the Department of Chemistry and Department of Physics, and also I'm a member of the Institute for the Study of Structural Matter. So also the name of the lab where I'm working is the Laboratory for Computational Modeling of Functional Material. It's a very long name, but I'll try to make it clear for you, and also to try to give you also some physical and some chemical insight into the materials that the two artists are studying in their work. So first of all, I'd like to introduce some, let's say, vocabulary. I'm interested in functional materials. It's a very simple definition that I will give you. It's a functional material is a material able to realize a function. And a function is a very diverse, it's a very general term to discuss, let's say, a biological function. It can be also a physical function like magnetism. It can also be light emission. It can also be light absorption, like we know very well for a solar panel. Sorry. It can also be conducting electricity for electronic application, but also we have, let's say, function for biomedical application, and these are drug delivery systems. Of course, this function is a response to an external stimuli. And in their, let's say, work, the two artists are studying the effect of temperature, but also the effect of light on how the material will be organized. But you can think about other stimuli, such as voltage, the change of pH, or the change of the concentration. I'm also mentioning in the title, in the name of the lab, computational. So basically, what we are doing in the lab is to use a computer to compute materials properties. And these material properties are very essential to define, for that we use computational chemistry and physics. And the field is also called molecular modeling, so these are synonyms. And so basically, when you are able to compute these material properties, you're also able to define the function of your material. So there is a clear link between the properties of your material and the function that you can, let's say, achieve. And so I like really to stress that my computer is a computational microscope. So basically, I can see on the screen of my computer, let's say, molecules, materials, and really understand their physical and chemical properties. So I can really probe, let's say, the matter and materials down to the molecular scale, and I can say even to the atomic scale. And this is very nice because, of course, this is very unusual, and I would say some of the most advanced, let's say, experimental techniques are not able to see the matter as, let's say, at this scale, at this atomic scale. And so I wanted to show you an example of the result of a research that is, let's say, a bit fancy. And this is a simulation, so it's a calculation showing how a molecule like a pentacene will, let's say, land on the surface defined by this material that looks like a football, which is C60. And so this is really the results of a simulation. And you will see molecule organizing at the surface of material. So you really can understand every elementary processes that are taking place in this situation. And you see really that the molecule going flat and then at some point standing up. So this is really based on let's say, interaction between these molecular materials. And you see now the layers growing layer by layer, and it's fantastic. I really like it. This is the work of one of my colleagues at the University of Bologna, Luca Mucci. And so basically with my computer, and because we get such a nice, let's say, computational power because of the progress in the computer development, we can now do computational experiments. So we can do experiment but on a computer. And now I'm switching to the field of research that I'm working on, which is called organic electronics. And organic electronics is a nice field that was established back in the 80s, where actually people discovered that organic molecules were able to conduct current. And so here the field is trying to develop devices based on materials that actually are made of abundant elements on the planets, such as carbon, nitrogen, and oxygen. And the device we try to make are energy-saving devices. So we try to somehow try to solve the problem of global warming, but using, let's say, a material made of abundant elements. And so you can really design very nice application, and one of it is these lighting panels. So basically, these lighting panels are made of organic materials, and the whole surface of the panel is now emitting lights. It's not just let's say a few points. It's really the whole surface that is emitting light. Another application is, of course, solar cells. And these panels are now, as you can see on the picture, they are flexible. So this is for the energy domain, let's say. But we also have, let's say, more fancy applications such as the OLED TV that you probably know from any supermarket. And this is more for technology development. The field also moved towards the L field. And now people, especially in Sweden, have developed this kind of biosensor to somehow monitor the temperature of a patient, the stress, the inflammation. And also this device on the bottom right is able to somehow monitor the level of glucose in the blood of the patient. This is for the F, of course. So yeah, of course, a little bit of chemistry because we are playing with materials, and in their experiment, in their work, they showed this very nice and beautiful, let's say, colorful videos. But everything is based on molecular materials. Don't be afraid by this chemical structure; they don't harm. And but what I want to stress here is that these materials that we use in our field have a special let's say, feature is that they are made of double bond and triple bond. So when you see a line that is double, that means that we have a double bond. And these double bonds are very crucial because without this double bond, these materials are not able to conduct electricity, not able to emit light, not able to absorb light. So that's very nice. And yeah, so the field of organic electronics tried to somehow replace inorganic material like silicon, like the different metals that you know, using molecular materials. And this is, of course, these are some advantages because especially the production of the devices should be low cost at some point. And these materials are really easy to process. As you see, this is a plastic foil, and you see the gray surface at some point will change color, let's say. Yes, it's coming now. So you basically, in this video, I showed you that we are able to print this material like you would print, let's say, a piece of paper. So this is super nice because this is actually, this plastic foil is actually a solar cell. So this, you could eventually, in the end, take this solar cell and install it on the roof of your house. What is nice as well is that you can make flexible device, and this is a light emitting device that can be folded in two. And in the end, you still see that it emits light even though you fold. And yeah, but of course, there is an issue that it's the performances. The performances of the device are not so good. I would say they tend to be very good. I would say, I mean, they tend to improve over the years, but they are not reaching the standard for commercialization. So, but still, we are using molecular material, and they are quite versatile. So I mean that you can take a molecule, for instance, and if it doesn't work, you can ask your friend that is able to synthesize new material in the lab, and go to the lab and synthesize a new one that maybe will have better performances. And now I move to the, let's say, the research topic that I've been working over the last, let's say, 7 years, which is about organic light emitting diodes. And so basically, organic light emitting diodes give you this very nice flat panel that can serve, let's say, as an alternative source of lighting, but also they can be used, as I told you, for commercial, for more technological applications, such as the OLED TV on the left, this mobile phone screen, and this extendable devices on the right. This is more for technology. Just a little bit about what is an OLED? What is an organic light emitting diode? Actually, it's a very complex device. As you see, let me show you what I'm going to. Okay, yeah, this. Actually, this device, the OLED, is a multi-layer device, and this is a very complex device. So, I mean, engineers are actually working on this device to make it more simple, but for the moment, it's still a multi-layer device. And what I'm interested in is the emissive layer, this part of the device. And this part of the device is made of two organic materials, one material that is called the host, and one material that is called the gas. And the organic light emitting diode uses a phenomenon that is called electroluminescence. So basically, what is electroluminescence? Is you just, let's say, inject a current into the device, and then you get light that is coming out. And so basically, if you want to make light, let's say, in this device, you need to inject charges, and this charge has to move in the blue material, which is the host, towards, let's say, the gas material where you have charge recombination, and then finally light emission. Of course, this looks very simple, and it's, yeah, but there's some, of course, let's say, competitive process that limits the efficiency of the device. And the efficiency that I would say the light that is coming out of this emissive layer can be characterized by this, let's say, quantity, internal quantum efficiency. But I would say not all the light that you generate in the emissive layer is going out of the device, because if you need to go from the emissive layer towards the end, the outside of the layer, you have to cross different layers, and this different layer can cause, let's say, a photon loss in the device. And so what we measure actually experimentally is the external quantum efficiency. That depends on a quantity, T, which is the transmission factor. And this transmission factor usually is around 20%. So basically only 20% of the light that you generate in this device is coming out. And these two quantity actually depends on the material that you basically fabricate. And so if you want to optimize the property of this device, you need to optimize the properties of the materials. And now moving towards the liquid crystalline material, because they have an interest for this organic light emitting diodes application. But just let's go back to the fundamentals of liquid crystalline material. So basically, I mean, you know very well liquid crystalline material for display application. This is well-known application. Also probably for really nice and fancy images that you find on Google Images with really, really nice color. And also probably from the work of DMITRY. But let's go back to some chemistry. So what is a liquid crystalline materials? Down to the molecular scale. So, basically, a liquid crystalline material is made of, you see, this material, this part of the material, which is made of double bond that I mentioned you earlier, but also from this R group that I will discuss in a few seconds. And these materials really look like a rod, basically. And these rods, they organize in this way. But you can also have material that looks like a disc. And you also see that we have these R groups here that I will discuss just after. And so you see that this disc-like, they like to form columns, basically. So if you need a column, you can decide to move to this material to the right, and if you want to have rods, you can choose the material to the left. And what are these are? Basically, these are long carbonated, let's say, chain. So there's no or few double bonds in this part of the molecule. So liquid crystal are material are everywhere, I would say. Of course, they are known for the LCD display, but you can find them also in cell membrane. So the phospholipids that are one of the main constituents of the cell membrane are also liquid crystalline material. The well-known cholesterol that I'm sure you know from your blood test are also liquid crystalline material. So you see that the cell membrane is really based on liquid crystalline material. It's also part of the cell. So the cytoskeleton is made of assembly of protein that form liquid crystalline phase. And recently it was shown that DNA, if you want to assemble DNA at a large scale, they also form liquid crystalline phases. One of the very nice properties of liquid crystalline material is their self-organization. So basically, if you just, let's say, put some, liquid crystalline material into a solution, they will tend to self-organize. So they organize by themselves. They like to be close to each other, if you like. And so we distinguish two categories of liquid crystalline material. The one on the left are the thermotropic. So basically, the way the material organized, so all the rod that you see on the picture is a liquid crystalline molecule, and so basically they change organization if you increase the temperature. So for instance, at the low temperature you get something very well organized, but as soon as you increase the temperature you get something that will be more disordered. And it's the same with the disk here at the bottom. A second category of let's say, liquid crystalline material, the lyotropic materials, and these materials are influenced both by the temperature and the concentration. So basically, you can change from a bilayer, and the bilayer is the typical structure that you see for the cell membrane. And if you increase the concentration of your material, you can get something that is called micelles. So basically, micelles are like spheres. Going to Wikipedia, and I did myself. So liquid crystalline material flow like a liquid, but are organized as solid. And what I can tell you also is they are anisotropic materials. So basically, their function, the function that I talked about at the beginning of my presentation, will depend on the direction you looked at. If you look from the side or from the top, you will observe, let's say, different properties and different function. And anisotropy is, of course, the opposite of isotropy. And so when liquids like water or different solvents that you might know, like oil, are, let's say, isotropic, let's say, materials, and they are typically liquids. I wanted also to show you a molecular movie of a liquid crystalline material. Because we do computational chemistry, we can do molecular movie. That's pretty cool. And so these are two molecules that are called phthalocyanine. And the phthalocyanine, basically, you can find them on the pigment of leaves. And so let's start the movie. So you see that my molecules are a bit shaking, let's say. The external part are moving very fast, while the center seems to be a bit more slow. So basically, at the end of the movie, I will explain you that the side chain that I mentioned you a few slides ago, this is the part of the molecule that brings, let's say, the liquid character of the liquid crystalline material, while the center part gives you the solid-like organization. And so again, I mean, to try to a bit rationalize the experiment, or let's say the work of EVELINA and DMITRY, I'd like to discuss anisotropy in the context of light interaction with matter. And so basically, I took this example of my, let's say, rod-like liquid crystal, and I shine it with light. Okay, and so there's a ray of light going through my material, and so what can happen in this case? And the light can be absorbed, completely absorbed, and this is what happened, for instance, when you go to the beach in summer, light is absorbed by your skin and you get suntan. And it can also be transmitted, so it means that the material is transparent to the light, and this is what happened when you shine light, let's say, on a bottle of plastics, the light is going through, basically. And the last phenomenon that can happen is reflection or scattering. And this reflection or scattering, it's highly dependent on the organization, on the anisotropy of your materials. So basically, if I rotate my material, so if I expose a different face of my material with light, the color of light that will, let's say, be scattered will be different. Okay? So I think I will stop here, and I would like to acknowledge a few people that have been involved in the work in the lab and all the nice movie that I showed you during my presentation. I would like to thank all the people from the group in Namur, also my friend Luca from Bologna, also my good friend from Alicante, Juan Carlos Sanchez Garcia, and people in Mons, ULB, and also in St. Andrews. And I would like to kindly thank you for your attention.
Thank you, Joann. Well, maybe you can join us, and I prepared some questions that have almost all been answered by your presentations. Yeah, no doubt. So I'll just try to. One thing is that what I found intriguing, this notion of the soap film that you also talked about. I found an article from 2019 in which was somehow published in the Wall Street Journal by Frank Wilczek, who said the gooey residue left behind in your soap dish is a liquid crystal, in fact. So, but both, well, you two and Joann, what you presented is actually going back to basics, because it seems to me that liquid crystal is now used for solving things or showing things, but it's actually at the core of life.
Absolutely. I mean, I would say while preparing my presentation, I discovered a lot of work in the biology related to liquid crystalline material. And recently I was in a PhD defense where one of the candidates was modeling, like using the same techniques that I showed you, a cell membrane containing millions of atoms, and showing that this cell membrane is actually a liquid crystalline-like material. I would say it's fascinating.
Yeah, but what you also discussed is, and which I mentioned also, this notion of twisting. And so that is recent research, you said.
Well, the liquid crystal was discovered when looking on a piece of carrot or a piece of fruit under a microscope in the 19th century. So
cholesterol cells.
Yeah.
So it comes from our observation of biological matter, and for us, this question of origins of life is very central to what drives our work. And of course, the ability of this organization of matter to be sensitive to light and to self-organize, it seems like these are two very important things for life.
Yeah, because in the 60s, you had Gustav Metzger, who developed, well, first he was interested in self-destructive materials, and then he changed and became interested in self-creative, so self-organizing effect. And he used liquid crystals in his liquid crystal environment that became especially popular when used in a concert by the Cream, the Move, and the Who in the Roundhouse in London in 1966. Was that an influence for you as well? You said you started looking at biological materials from your background, so maybe not directly, but was it an influence eventually, or
Well,
not really?
as you mentioned, this was an unusual work for Metzger, and both as a thinker and as an artist, I would say that his work is extremely distant from ours. I mean, philosophically very different.
Yeah.
Albeit, I think that the liquid crystal environment was a very important artwork for its time. It was resurrected not so long ago at the Tate Modern, and
they acquired it into their collection. So I think our works are still very far away from being acquired by major museums, just because of their very ephemeral nature.
Yeah, because you also move away from the object of
exactly,
art.
exactly. So they're very counterproductive for the preservation department in the museum. But we used to teach art science at the Royal Academy of Arts in The Hague, and one of our students, she did a beautiful work with liquid crystals, which is kind of the next step from Metzger's work. And what she did, she just put a projector lens, and she had the liquid crystal slides in real life, but instead of looking in a microscope, you would see a beautiful projection.
Yeah.
And she's not a well-known artist, but it was a beautiful work. And another great example of contemporary artwork and artist who is working with metamaterials, liquid materials,
liquid crystal, photonic crystals, hydrogels,
is Yoon Kim. And he's a Korean artist. He was based in Europe. Now he moved back to South Korea, and he had a residency at CERN. And I think last year he was representing Korean pavilion at the Venice Biennale. So you can, if you look Yoon Kim, you will find his work. And
his work was presented in nearby Brussels not too long ago at the
EMAL. So it's extremely beautiful work, exploiting exactly this man-made, very special function materials, and he does it in a very poetic and technically excellent, extravagant way. So definitely this continues in the arts today.
Yeah, Nikki Asman, who was in our last laser talk and who is also shown in the festival, also uses soap films in some kind of way related to sun research. I've maybe a question for you, more or less. I'm not sure, or both for you, because I was sort of looking because it has such a, well, we are all made of stars is the usual expression, but liquid crystal seems to have a really science fiction kind of character, and I was trying to look it up whether there was a link, and I only found it back in the title of a sci-fi political thriller. It's called, which I haven't read, Liquid Crystal Nightingale by Eileen Lee. I don't know if anyone in the public has ever read it, but do or have liquid crystals been used in science fiction that you know of? I mean, the examples that you gave, like the foldable screens that we're now slowly getting used to, and such, and the film especially to control any kind of health issues, become very close to science fiction. But
Indeed.
Do you have any other predictions?
I would say also that let's say especially liquid crystalline material would be interesting for, let's say, the bioengineering, especially because they can be made, let's say, biocompatible. And so because they can really adapt their shape, they could adapt, let's say, to the skin, or even be the brain. So they could be interfaced with the brain.
They could be implanted.
Yeah, exactly.
Yeah. Which is kind of funny because if we're talking about finding solutions nowadays, we're going back to the origins and then implanting something which was there all the time anyway, or is already integrated, but then sort of using it in yet a different way.
I would say that these are, let's say, published work, so from recently, and I know people, let's say in Stanford, for instance, working very hard on this topic to try to make, let's say, e-skin. So really electronic skin.
Oh yeah.
So that makes, like you could have, let's say, like a patch on your skin that could be addressed with the electricity. So that could, let's say, for instance, control whatever you want, or you could, let's say, read information from the e-skin. Or for instance, people having like Parkinson's disease, you could think about implanting this patch into the brain and, let's say, inject a current somehow to control the Parkinson's disease.
Could that also be connected to eyesight, or?
I don't know, but I don't see an issue to that.
Yeah. What I was intrigued with in your new projects and what you showed the microscopic film, but that you said at some point that you were also intrigued by how you could see something microscopic with the naked eye.
Yeah, absolutely. I mean, that's an ongoing trajectory in our work. I mean, from the very first piece that we showed with sonoluminescence, the imploding bubbles of air are microscopic, and the reason that we can see them is because they emit light, and because there are quite a few of them, hundreds of thousands of them collapsing in front of your eyes. So there's a vast variety of optical means to observe microscopic phenomena, even nanoscopic phenomena that have to do with very, very careful sculpting of the environment. In the case of, I return to that example because there in approximately 60 liters of water, not only are you seeing the light from these bubbles because that light travels to your eyes in a very short distance, but also because the environment itself is a gigantic magnifying glass. A big sphere of water magnifies what is happening in it, and you don't need to add any kind of ocular. There are techniques such as we only briefly address because we would have to go into quite some technicalities, but with the piece with soap bubbles, the soap bubble membrane can become as thin as a single molecule, and that allows this leap in magnification to arise. It also becomes a lens, and for that matter, a lens that allows you to look at what is happening as a 180-degree projection.
And get rid of the interface of the microscope.
Exactly. And get rid of the screen, etc.
And it's not that we want to get rid of the microscope, but today's science is going into these domains that are very difficult to reach without special tools and special culture, being prepared and being versatile in this. However, if you are, as a human being, as an animal, as just as part of the universe, you are confronted with some phenomenon, just like a liquid crystal reacting to light. You will immediately figure out this phenomenon and how to interface with it. So you can explain in many, many words what are liquid crystals, but if you can observe their behavior, you don't need explanations. So in a way, experiencing things directly, this is how science started. And because of these very sophisticated tools and very sophisticated scientific culture that exists today, normal people are being cut off of enormous intellectual wealth
Mm-hmm.
of knowledge that is created not by a group of scientists but by our civilization. So and since our senses are still extremely versatile, extremely fluid, so we can also develop new senses. We can
Again, this notion of
fluidity.
Yeah.
Yes, the fluidity of the brain to
Mhm.
like and we've seen it in evolution of life many times, how it can develop new senses. And if you look at some when we were working on sonoluminescence, we discovered this creature, mantis shrimp, that has the most sophisticated sensory apparatus in the animal
The
kingdom,
most sophisticated vision, yeah.
that we know of,
Mhm.
because it can see in infrared or ultraviolet. It has trinocular vision. It has 16 different types of cells sensitive to different wavelengths, and we have only 3.
You
Yeah.
can also see the polarization of light.
Yeah, so you can evolve your senses.
Yeah.
And you can only evolve them through interacting with reality, with physical reality.
Yeah. So you say things can be implanted, and you say we can develop it ourselves.
Well,
in
I
a
don't
way,
see.
or it can be a combination of the two.
It certainly can be a combination of the
Yeah.
two. I mean, not that that I have anything against cyborgs. I think that we live in a very cyborgian reality
if
as
you
it is.
don't have your own intentionality, you will be manipulated.
Mhm.
So
You will become a cyborg
it
regardless
will
of
come
Yeah, yeah,
from,
we want to
from the
intention.
outside.
It's interesting how our talks, one way or the other, are all interconnected, because our next one is about restoring the human element, but also in view of artificial intelligence and such, which is the 9th of November at the Royal Academy of Antwerp, if you're interested in that. So maybe it's time to answer some questions of the audience, if there are any questions from the audience. Or are you all flabbergasted by what has been presented? Yeah?
Just a question about the first video you showed, about this light bubble. You said it was a laser beam inside, but I have quite a matter to understand how you were able to project everywhere in the room, in the space.
By the way, if you are interested in this work, it's a work from 2007, but we still do perform it sometimes. And on the 18th of November, we will perform it in Delft, a city that is very famous for its optical innovation.
Yeah.
In the last 400 years. So at the TU Delft, we do the performance of 10,000 picofeathers in foaming acid. And another amazing thing about soap film, that it can act as a light guide, as an optical cable. And we make, in fact, this piece is best performed in a planetarium or in a space that has a shape of a soap bubble, of a hemisphere, because if the laser enters at the right angle, it will spread in the bubble and will create the projection.
It is not a phenomenon that you can just imagine, because it was actually not so particularly long ago that it was discovered. It was in the early 2000s, and we discovered it more or less at the same time as a group at the Lemniscate Institute in Moscow. We encountered their paper some years after we started conducting our own experiments. And what is especially difficult to fathom is that when this single laser beam enters, it breaks up into very, very thin, as thin as a single micron, optical tracks that are surface waves that the light carves along the membrane. So when you look at it, and be it in the form of a projection or directly on the soap bubble clusters, it's totally unfathomable. It doesn't seem, there are no analogous behaviors. It's very, very weird.
And when we started developing this piece, yes, we came along solitons, this very interesting things, surface waves, and they exist in quite microscopic domains. But in in this work, you can actually see them happening in the projection if you know what to look for. So once we invited a physicist with whom we work in Amsterdam to see this performance, and after he saw it, he said, "Oh, there are so many things there at once overlaid." So you see this kind of nonlinear optics phenomena, you see interference patterns, you see molecular chains in the soap film, and it's all overlaid together. And another very gratifying visual morphology that I personally appreciate about this work is that creates this non-Euclidean spaces, this kind of spherical architectures, this curved architectures, and spaces that are modeled with this curvilinear structures that are very synonymous to how light travels and how light can be bent. And you're finding a perfect sphere is not so easy in nature, but somehow a soap bubble, the bubbles, the foams, they give you this lovely interface.
What I liked, you have a question?
Oh yeah, just
Yeah,
possibly
yeah, go
on-
ahead.
on
Yeah.
the subject.
Yeah.
For the laser you use, like a special kind of laser, or is it like any other laser you can find on the market?
Well, that's a key question, because actually when we started working with lasers in the early 2000s, late 90s, early 2000s, they were prohibitively expensive, and so the kinds of continuous diode lasers that we use now, we have used some what are called entertainment lasers, which are only different in the sense that they scan. But the scanning got in the way of certain functionalities. So we at this point in time, we just get the diodes and we build them from scratch, because we need to they have to have a certain functionality, but more often than not, we need quite a bit of power that, especially if you're projecting in a planetarium-sized space, and magnifying such microscopic dynamics, you need to have a rather powerful laser.
But you can do all the same things with a scanning laser. And the first time we did this performance, we did it with a very weak laser, but you can still observe all these phenomena.
So what I really liked was that you put the work of Evelina and Dimitri in your presentation. So was it an eye opener for you when you saw their work, or because as what you said about the physicists who saw your performance, who said, "Oh, there's a lot of things going on at the same time"? Was it similar for you?
It's really exciting, because it's like when you see things that you don't understand as a scientist, you want to understand, and you want to try to rationalize what is magic for anybody. And so I tried, to let's say find some explanation, of course, but it's very complex, I think. First of all, there are many phenomena involved, and I mean, to be honest, I don't want to give a definite answer to what I see, because I think there are many more phenomena involved, and I would have to know what are the exact conditions where when they perform their performance, let's say, and before getting into the answer. So it's very complex.
Yeah.
And
so
we are
need to go to the performance in depth.
Exactly.
Yeah.
Also, as a scientist, you always want to be careful when you want to explain something.
Yeah.
Because it's not always the simple answer.
Yeah, but you don't necessarily. I mean, you gave a wonderful talk and you can explain things very well, but you don't. Do you really want to explain? Or it's also an immersive experience for an audience, or not?
For sure. No, we are. The last thing we want to do is for the misleading nature of words to taint an observer's experience. And if anything, we prefer for people to approach the scientific background of an artwork afterwards.
Mm-hmm. Yeah.
And in general, I don't think there's any need for popularizing or disseminating scientific ideas. There's a very sophisticated agenda that is doing that without anyone's intervention. However, we do want to rouse people's curiosity and to ignite their perceptual processes. I mean, we think that the purpose of science is very, very parallel to the strife of art, and that is to sharpen human perception. To
develop a human being and not to create a new vacuum cleaner.
Yeah, yeah. Well, that's a really nice way of maybe finishing this talk to not develop a new vacuum cleaner, because we have more than enough of those. Unless there's still another question in the audience. No. Then I guess, unless you have to say something else or you want to make another comment, then I would like to thank you very much. I would like to thank the audience and KIKK Festival, and I'll enjoy the festival. Thanks.